Good afternoon, all. Welcome to the December 13th issue, or not issue, but webinar of Foresight Synergy Network, last event of 2023. My name is Peter McKinnon, and I serve as the chair of FSN. Today we have Peter Chapman, who is going to share with us his long-time exploration of quantum physics, as seen through the eyes of an accomplished electrical engineer. He's not a physicist. I make that point just to give you some background. And he's a graduate of Imperial College, London, UK. Peter worked in microelectronics, defense research, and telecommunications, particularly the latter is much of his latter part of his life. He was a player at Nortel, and in fact was a member of the U Ottawa team that investigated the collapse of Nortel, a 6-year project. Peter's become I guess we say in his retirement a serious time spending looking into the what he called originally the weirdness of quantum mechanics. So over to you, Peter.
Okay, well, thank you for that, Peter. Yes, So my interest in this started, I suppose, like all of us in physics high school. You know what's going on, and we were told by our teachers that there are things there that are weird and that possibly can't be explained by conventional methods. And then from then on, my next interaction on that I remember very distinctly was when learning about microelectronics at university in 1960. Well, I graduated in '66, so it'll be around that time. And the professor explaining that in quantum physics, if you make an observation, then it freezes what's a probabilistic or indeterminate state. So I asked the very, I thought, sensible question of him, you mean if I'm not observing, my transistor won't work? And to which his reply was, stop wasting my time. And I think that reaction, it really sums up what I felt about why we were not willing to address what were then regarded as some of the strange things in quantum physics. And to be honest, that was 1966, and it hasn't changed a bit between then and now from everything I've observed. I'm going to show you just the next chart. You see this pile of books here. That's just the books that talk about quantum physics that I've studied, and if anything qualifies me to give an opinion, that's what it is. I'm not a physicist, as Peter said, but I've read all these books, and as well as those, I've read many hundreds of papers online, and I'm still at the position where I'm not happy that we've got anything like a definitive view of quantum physics, and I think we've still got some really bizarre ideas floating around, which I'll just share with you briefly today. Now, if you question the modern physics interpretation, it doesn't mean you're an outsider, although I will talk about Paul Marmé, who's a very well-known, or he was a very well-known physicist here in Ottawa, who sacrificed his career basically to oppose what is considered to be the conventional view, or sorry, the established view of quantum physics. Einstein himself rejected much of the what's called the Copenhagen interpretation of quantum physics, and was actually sidelined during his last few years at Princeton as a result of that. Erwin Schrödinger, whose name is attached to one of the most famous equations in quantum physics, also had a problem with it. Niels Bohr had some issues with it. As I said, I'll talk about Paul. I don't know if he pronounced his name Marmé or Marmet, but he's French-Canadian, so I'm assuming it was Marmé. He was actually at Laval and then subsequently at Ottawa U. I think my approach always has been and still is in the last few years to take the Sherlock Holmes approach, as I call it, rather than take things as we're being told on face value. I mean, Sherlock Holmes always, I don't know if you know the background to Sherlock Holmes and the character. It was based on Sir Arthur Conan Doyle, who wrote the books, was a medical student in Edinburgh, and his professor and his mentor was this pathologist who examined why people had died. And his pathologist's philosophy was, you don't assume anything. Assume what you only base your decision on what you actually know or see in the way of evidence. And that's what that's what led to the philosophy through those books. Having eliminated the impossible, the improbable, however improbable, must be the truth. The problem with quantum physics is that, and I'm going to basically summarize, the people who study it for a living seem to be more interested in making it weird, magic, and I almost sense there's a feeling that they want to keep out people like me, you know, physics hobbyists. If you go onto a number of websites, they will caution you, and I've seen this, not to email them saying that what my decision or opinion is until I've got like 20 years of experience of researching it in an academic institution. In other words, it seems to be something of a closed shop where this whole idea of weirdness is something that's that they seem to continue with. There are four models that I'll just briefly talk about. The Copenhagen interpretation dates back to the early years in Copenhagen at the Solvay conference, which was an annual physics conference, and primarily in 1927 when it was Heisenberg and Niels Bohr who came up with the model that is still very, very popular today. And it depends on probability waves and the idea that multi-states exist until observed, which I'll talk about a bit more in a moment. There's also something called the many worlds interpretation. This is as bizarre as any science fiction writer could ever create, where the assumption is that the universe splits into two every time somebody makes an observation. I personally don't think it's worth any more time than that observation. I will share with you, though, that if any of you are planning to invest in D-Wave, the quantum computing startup out in Vancouver, the founder of D-Wave believes in the many worlds interpretation. There's also something called the transactional interpretation, which is where it actually talks about time reversal. And again, I'm not going to get into the technicalities of it. And again, it's got a legion of followers, although not that many. And there's also something called the wave theory of matter, and this is the one that I'm more inclined to have confidence in than any others from all of my researches, created by the primary leader of that is a guy called Milo Wolf. I'll talk about his book in a moment. So anyway, let's just carry on. Oh, sorry, I went the wrong way. The point about quantum and the reason it's so different from what we'll call classical physics is we can't observe anything in the quantum world. And it's that fundamental idea that I think is a stumbling block for many quantum physicists. They want to observe because they are having difficulty dealing with the information if it can't be observed. And they keep, you'll see if you study many of the experiments, they've tried to create ways of observing a quantum state. And in many cases, that's not what they've actually achieved. What they've actually achieved is something that may be probabilistic, but it's not actually an observation of a quantum state. Again, I don't want to get into the technical details of some of these experiments because they're extremely involved. But if anybody's familiar with Plato's Cave and the philosophy there, and it's Aristotle wrote it, the essay, it's worth a read because it really addresses human behavior and how we behave when we've only got certain limited information, and how not only do we build our ideas of the real world from that limited information, which is what we need to do, but how people are unable to, when some of that information contradicts their intuitiveness, how difficult they find it to actually overcome that. The point about quantum physics is we can't observe any quantum particle. We can't observe a photon of light, not as such. We can't observe an electron in transit as such. We can only observe its interaction with our observable, much bigger world. As an electrical engineer, I was introduced to this concept. We deal with electromagnetic waves all the time, of course. Wi-Fi and phones and everything we do is based on them. We can't see an electromagnetic wave, and we've never even addressed that we should. What we can see is its voltage in an antenna, a dipole antenna typically, and we can turn that voltage into a charge on something which we can then sense with a voltmeter. So we see with our eyes something on a dial on a voltmeter, which is many, many steps separated from the electromagnetic wave. But because we believe Maxwell's equations, which define electromagnetic waves, are totally consistent and we believe them, we're able to make assumptions and measurements on the electromagnetic wave, but it's based not on seeing the wave, it's based on an observation of an artifact that it causes. We trust our instruments, in other words. The problem in quantum physics is we don't really have yet those instruments that enable us to make those same assumptions. Let's just because of the order of my charts, let's make a brief aside into Paul Marmé. He said there is not much hope, maybe you can read it, but try writing new papers. He basically says your career is over if you question the Copenhagen interpretation. And Paul himself was forced to resign. I won't read this one, but I'll just tell you what it says. He was forced to resign from Laval, and they actually evicted him from his office. And subsequently, he lost all of his funding. And this is all because he signed an open letter advocating against what's called the Big Bang in cosmology, which is a similar idea. By the way, if you look on my chart, you'll see a note. Neil Turok, who Peter and I know, and I think many of you others have met him, also he dismisses the Big Bang theory. And the Big Bang theory was, just for your information, was created by Fred Hoyle, an astrophysicist, to ridicule the idea that the universe evolved out of nothing. We have similar things going on in quantum physics. Paul Marmé's book is out of print and difficult to find, and I won't again read this, but I'll just tell you, it's considered one of the classics in questioning exactly the subject we're talking about today, questioning the current thinking on modern physics. It's reputed to be available as a free ebook, although I have to be honest, I looked the other day while putting these charts together and I couldn't find a link to it anywhere, otherwise I would share it with you. It's out of print, and you can possibly find a used copy at a great price. I do actually have a copyright issue, I have a photocopy of the book, complete, but for copyright purposes, I obviously don't want to share that too openly, but it's an interesting read. It's not a very long, it's a very small book. And it's definitely, if anybody's interested in the subject, it's worth reading. Okay, back to back to where we are with physics. Now this is what I just talked about, Maxwell's equations, so I won't spend any time on this. But it all comes down to this idea that there's a probability function. Now this comes out of some of Paul Dirac's original equations, where he used a complex number to define various artifacts of an electron in space. And the problem with the complex number is it's just that, and you can't really use it for any, you can't relate it to the physical world. So what they did, and I say they, he and others, they determined that it was related to a probability function, and by squaring the complex matrix, essentially, you can reduce the complex numbers to linear numbers, and that gives you something that's identical to a probability function. They therefore made the assumption that there was a probability function controlling the state of the electron. Now, there's no other rationale for that other than it makes the mathematics work. And the issue here is, what they're doing is they're saying, they've come up with mathematics that seems to describe what they're looking at. They're then doing something with the mathematics and assuming that the mathematics is telling them what's really going on, rather than just as a tool to be able to make calculations about it. And this is what led Einstein to his famous statement that he said, basically, God does not play dice. And he was rebuked, I think it was by Bohr, who said, do not tell God what to do. And then Stephen Hawking, who then went on to say, not only does he play dice, but he does so in the dark, which again, is a view that's widely held. Einstein never bought into this idea of a probability function, and he and Schrödinger came up with this Schrödinger's unfortunate cat. The idea of the thought experiment was that you're probably aware of this, but it's that there's a poison which is in a container which is triggered by something in a Geiger counter. The Geiger counter is dealing with the probability function, and therefore the cat is either alive or dead, depending on whether the Geiger counter triggers the poison gas to poison the cat or not. The point about this experiment, or this thought experiment, is that the Geiger counter only makes its trigger when somebody observes it, according to the theory. And as a result, the cat is neither alive nor dead until somebody observes something in this state. And therefore, the cat can be in this indeterminate state of being neither alive nor dead. Now, a lot of people, as I said, Einstein and many others have a lot of problem with this, and I certainly do. Just going to go forward a minute. Now, change of state. What is an observed change of state? I've talked about this, and I was asked by actually a physics professor who was given a lecture at Ottawa U of an example of a real world situation where an observation can change a change of state. And it comes down to what you mean by a change of state. And this is the model I came up with: a lottery ticket on a desert island being sold by one person to the other. The state of the lottery ticket, and I mean the state is the value by which you are willing to sell it, or what its worth is, depends on a piece of knowledge, and it depends on a piece of knowledge of of the result of the lottery. The change of state it takes place not when the lottery is drawn, but when the person knows the change of state, and that is the thinking that's led us down this disastrous path in quantum physics. So. Anyway, I've mentioned mathematics, I've mentioned Schrödinger's cat. Niels Bohr, I won't talk too much about him again, I'll leave the charts with you and you can read what's said there. Carl Sagan has said similar things about the problems of what we're observing, and Heisenberg himself, who's famous for his uncertainty principle, which I'll mention again in a moment. So what do we mean by uncertainty? Well, I've said this before, he never actually called it uncertainty. He actually called it, and the German translation is either unknowability or indeterminacy. Unfortunately, it's been taken by the world to be uncertainty. And it sort of frustrates me somewhat that whenever I say I'm doing something about quantum physics, you invariably get someone making a sort of silly joke about, oh, how certain are you, or how uncertain are you? Because what they've heard in the popular world out there is that quantum physics is so strange, nothing's certain, and everything's sort of up for grabs and can't be known. That's not at all what Heisenberg's uncertainty or a principle said. What it said was that if you've got various parameters that you're measuring, if you define one very, very precisely, then what you leave is a certain spread of parameters in one of the other a certain spread in one of the other parameters. And we use this daily in what's known as the Fourier transform, which is used in signal processing and many other things. This is an example. This is I'm showing you a diagram here of a Fourier transform. The top one, actually, the top pair, is a discrete cosine transform, which is a subset of a Fourier transform, and it's what's widely used. I don't know if people are aware of this. If you look at a JPEG photograph, all the time, just about every photograph you take with your phone is a JPEG. That uses a discrete cosine transform, the Fourier transform, to filter out the information and reduce the size of the file. It's used widely in signal processing and voice recognition, as we were talking about earlier, and it's used in many, many other things in human life. There's nothing uncertain about it. It's a mathematical way of putting it. To describe it simply, The left and right diagrams, look at the one on the left. If that's a time varying function, say a voltage on a wire, and it goes from 0, 0, 0, it suddenly goes up instantaneously to another value and instantaneously down to another, then its frequency spectrum is the one shown on the right. And these two are reversible. In other words, if the one on the right is the voltage in the wire, then the frequency spectrum will be on the left. That's its Fourier and its Fourier function and its transform. And what this means is, in the quantum world, if you're looking at a wave and some artifact, then you can't define. If you the one on the left, the instantaneous, nothing can change instantaneously in the physical world, so that doesn't really exist. All you've got is some indeterminacy about the exact start time and top. And after the event, in fact, you can, in the case of a waveform like this, after the event, you can actually determine where the middle of it was by measuring in time its value symmetrically, and then you can say mid-time between the two. But you can only do that after the event. And that's really what this Heisenberg uncertainty comes down to. And again, it's much more technically complicated than this, but it's not this idea that something can't be known. It's this idea that by trying to know it, you're really trying to ask the wrong question. I mean, I'll just take an aside to mention a little anecdote about particles and waves. Well, let's talk this. Sorry. There's this thing called particle-wave duality, which is, I think, one of the other big problems that we get into with quantum physics. It all started with the what's called the ultraviolet catastrophe. Back in, I don't know if you know, but Einstein actually got the Nobel Prize, not for relativity, but he got it for the photoelectric effect. And one of the things that happens as a result of the photoelectric effect is that light is given off a hot source only in what appear to be discrete packets. And as a result of that, the theory said it shouldn't be like that. The theory said it should be continuous, and it should actually favor short wavelengths or bluer light than red light, and that's exactly what doesn't happen. Above a certain frequency, there is no emission at all. So in order to get around that problem and not really address the fundamentals of the theory, they came up with this idea that light can only be given out in certain discrete packets, which is true, and that seems to be supported by many, many experiments. And that we call it a photon, and so on. And the other point about this is the only way you can detect light is by raising an electron from one orbit to another. And as a result, or by emit light by it dropping down from one orbit to another. That's why we get this concept of a photon. People then assume that light then consists of discrete packets which cannot be subdivided. And herein is the mistake, because we don't know whether that packet can be subdivided or not. But if we take the fact that maybe it can, and I use the example of my greengrocer. You know, my greengrocer can sell me a pound of apples, and because he's only got pound weights. And if I want one apple, he can't weigh it, so he can't sell it to me. So he only sells me a pound. But once I've taken the apples home, he has no control over whether they can be subdivided or not. I know that sounds like a trivial example, but the idea is to get people to think about what does it really mean to talk about a particle or a wave. Now, there's one very famous experiment which I'll just explain because this is important. If you send light at two slits in a screen, if it's a particle, you would expect, and look at this diagram now, you'll talk about Bourne's machine gun, you would expect the effect to be what you get at the top. Some of the particles go through one hole and some go through the other. And the intensity you would get is the three screens on the right. What you actually get in reality is the bottom of these, which is a spread such that they are identical to water waves, which is what you get if you put two waves through holes. What does this tell us? Very simple experiment. Anyone can do it. It tells us that light is not a discrete particle once it's left that source, that it can actually be broken into a different, it can be broken into smaller quantities than the original photon. Once you accept that, all of the nonsense about particle wave duality disappears overnight. It's as simple as that. And this is a very fundamental experiment that describes it. Getting back to what we're really talking about, why will the physics community not accept the simple result of this experiment? They seem to be not willing to even consider it. There's another experiment, which I'll just talk about, which more or less says the same thing. This is a half-silvered mirror where you can see that light on the left is hitting a half-silvered mirror, and some of the light goes through it and some gets reflected and so on, and then they're recombined at the end to come out the other end. Physicists will tell you that the photon of light probabilistically goes one way or the other, and they don't know which, but somehow they manage to come together at the end and recombine probabilistically. No. If you accept that the particle can be broken up into half and half, then this is absolutely explained with common sense wave theory. The thing hits the half-silvered mirror, half of it goes one way, half of it goes the other way, and you recombine them at the other side. Now, the other thing that's interesting about this, and we know this, is that you can't detect half of a photon of light. As I said, you've got to be able to raise that electron level. You can, however, detect two combined half photons of light. And we know this from the very simple fact that you can see a distant star. If you couldn't see a distant star, the light, this is Andromeda, by the way, which is believed to be the furthest thing we can see with the naked eye or among them, giving out an awful lot of photons or whatever light, of course. But if you couldn't combine them in our eye, you would not be able to see very, very distant stars. You would see them sometimes, and you wouldn't see them consistently. And yet, two people standing side by side can always see the same pattern of stars permanently and forever, which tells us that the combination of light is absolutely something that happens. So here we are. We've got this fundamental idea that you can't break up light, and it leads to all sorts of a photon into less than a photon, and yet we happen to know from two very convincing experiments that all of the problems go away if you accept what these experiments seem to be telling us. The problem that I'm having is that the world is not really willing to accept that idea. I won't talk about the half-silver mirror anymore. Double slit experiment. Just looking to see how we're doing for time. Now, entanglement is another of these ideas. The idea of entanglement is where a particle, well, you can back up slightly. You can create pairs of particles which are highly correlated, be they electrons or whatever. The point about the particles is that once you separate them from their partner, the idea is that because whenever you try and measure something about a particle, you destroy it. The idea is that by generating a pair, you measure the characteristics of one, and it tells you exactly what's happening with the other one. Now, again, the quantum people will tell you that these things are changing their characteristics in time. Therefore, when you measure the characteristic of one in time, you are essentially measuring the characteristic of the other one, which is correlated with it, even though it's physically distant. In other words, that you've got some, what Einstein called spooky action at a distance. You've got some way of determining what's happening at something that is distant and not connected from an information perspective with what you're measuring. And this, again, is this is only an issue if there's a probability issue, which is what I mentioned earlier. If it's not a probability issue, if it's actually we just can't measure it, and it's the probability idea has gone away from it, then the entanglement problem goes away. So again, here we've got what's many regard as a physically impossible situation, or something that implies that the whole universe is quite different from how we observe it, being contradicted in order to fit it to this strange idea of entanglement, rather than re-evaluating whether the entanglement is actually valid or not. So this brings me back to my main point, which is I don't understand, or I do understand, I suppose, why the physics community continues to find ways of coming up with universe splitting, time reversal, or all these other things in order to fit them to these weird experiments, rather than taking, the Sherlock Holmes approach, which is, well, it's all very well, but the evidence tells us that it's a lot simpler than that. Occam's razor principle, I suppose it is. There's another strange, experiment called Bell's inequality, which is quite famous. And what he does in Bell's experiment is, again, using these correlated particles, you send them through two filters, and you get 50% of them are showing spin in one direction and 50% are showing spin in the other direction, which is what you always get, because it's an arbitrary, it seems to be an arbitrary issue that you can't have any control over. So you have two of these correlated particles go in and hit in the filters, and then you displace the filters and put an error in and you say, well, you should get a difference of 50% when you do that, assuming, of course, that the spin of these things is some way related to the alignment of the filter. That's the assumption. Again, you have to go back, and the result you get, by the way, is that if you put an error in, you still get exactly 50%, however many times you do the experiment and however many times you run it. So the point is, you have to go back and say, well, there's something wrong with the theory here, not there's something wrong with the experiment. The theory tells us that if you displace the filters, you will get it, and you should get a number other than 50%. You don't. You always get exactly 50%. So the underlying assumption is wrong. And the underlying assumption that is wrong is that the filter alignment is somehow related to the spin of the electron, when in fact it may not be. It may be just a binary state, red or green, whatever, up or down or whatever. And all that the filter can do is determine, yes, it's possibly that way or possibly that way. In which case, your results, the 50% results, would be exactly in line with with what you're seeing. So I suppose what I'm saying here is that the whole physics community, and I put a whole lot of people into that category, seem to be more willing to find weird, magic, things that defy common sense, rather than look at the results of the experiment and really go back and re-examine the fundamental assumptions that have been made in order to do that. What does it mean for quantum computing? And this is really where. Okay, let me back up slightly. When I was working at Nortel, one of my tasks was to explain quantum cryptography, or quantum data transmission, and how it can be made secure using quantum communication technology. So I did quite a lot of research into this and presented it to the executives. The fundamentals are that in quantum communication, you send light packets, as they are wave packets, down an optical fiber, and you send them digitally with a certain orientation. Now the way it works is you can have what I'll call horizontal and vertical orientation. That's one set of axes, or you can have diagonal orientation. That's the other set of axes. If you measure them using a filter with the opposite axes from the one it is sent with, you will get a totally 50% wrong half the time result, just because of the way what's called the orientation of these things works. And once you've measured it, once you've measured a photon's orientation, that's it, it's gone, you've lost it. And this is the fundamental difference between all of quantum observations and real world classical observations. So what you do is you send these, you randomly select the sequence of your filters in terms of how you send the photons, and the person at the other end also randomly selects their filters for receiving them. And then at the end of the communication, you then compare the ones that you sent and the ones that the person at the receiver sent, their random sequences, and you only use the ones that agreed, you discard those that didn't. And you can show, and there's a very famous algorithm that came out of actually the University of Montreal, which can show, it's known as BB84, you can show that you can actually recover the information by doing that. The reason this is a very powerful tool is because if there's an eavesdropper listening in, who's listening to those photons and reproducing them again to retransmit them, they will not get the same result, even if they know at the end of the day which were the correct and which were the incorrect filter alignments. So you have a way of knowing that your communication has been listened into, and it's proved to be absolutely robust. So that works. That's not really quantum computing, that's quantum communication based on a very simple idea that once you've evaluated the orientation of a photon, you've lost it forever. And because of this other feature that if you've got the axes wrongly orientated, you will get a 50% wrong idea. That brings me on to massively parallel factoring. The idea of this probability function, and something is only in a state once you've observed it, leads people to believe that you can have a system whereby it's in many, many undefined states and until you observe them. And this leads them to the idea that you can then have a massively parallel computer. And the massively parallel computer is the holy grail of computer quantum computing, because it potentially, if it could be done, would be to break cryptographic codes using something called Shor's algorithm, which I again won't go into today, but it's widely available to look at. Quantum computing, it can only work if it is possible to hold those indeterminate states and then make an observation and freeze one of them when you do so. The Schrodinger's cat problem and the other problems of probability functions. If the probability function doesn't work, and it doesn't work, for example, if some of the things that we talked about, some of the earlier experiments, some of those assumptions are not valid, then basically the massively parallel computer isn't possible using today's investigated techniques. And I am very, very skeptical that using the techniques that are being addressed today can ever be made to work in a massively parallel computer. I know that there's massive amounts of investment and government funding and all sorts of people looking at this, but it's worth looking at one of the many books, and I've read many books on quantum computing, and they all say the same thing, essentially. We're a long way away from doing it today. Anyway, it's just, this is, I just took this, using Shor's algorithm, this is what we can basically expect to be able to, in a classically massively parallel computer, as soon as your number gets bigger, then the time gets to be impossible. The reason for factoring, by the way, for anyone who's not familiar with cryptography, is almost all current cryptographic systems do depend on being able to factor large coprime numbers, particularly. And if you can do that very, very quickly, you'll be able to break cryptographic codes. And this is as I said, it's the holy grail. It's also the worry of cryptographers, and which is why there's so much interest and investment being made in it. Okay, I'm just going to talk to you about a little bit of the reading. I'll just share with you. I'll just share with you something. I'm just going to read this because it's not on the chart, but really, back in this is back in October 2009, when there was a report of an experiment indicating that something can be transmitted in faster than the speed of light. And this is my comment as published in the New York Times, actually comments. The problem with this experiment and most other ideas in modern physics is that the physicists get into the isn't quantum science weird mindset and lose sight of the limitations of observability. Quantum mechanics, despite being created by some of the greatest minds of the last century, is poorly understood even by experts. We cannot see particles. The concept of seeing a particle is meaningless. All we can do is observe the effect of a particle interaction. This is where we get into trouble. We assume that the interaction tells us everything. It does not. Because elementary particles obey the same mathematical analysis as randomly driven events, we assume they are randomly driven. There is no evidence for this other than the commonality of the mathematical analysis of the effect. Einstein so eloquently put it when he said, "Quantum mechanics is certainly imposing, but an inner voice tells me it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secrets of the old one. I, at any rate, am convinced that he does not throw dice." And then I went on to go talk about the electromagnetic wave that I talked about earlier. And at the end, I said, we know very little, and don't let those physicists tell you otherwise. I'll just share that with you because it got a lot of comments. If you write a comment to an article in the New York Times, people like it or dislike it. I got a lot of likes for that. So obviously it's a view that's being shared out there. The other thing I just wanted to share at this point was I'm going to talk a little bit more about going back to talking about Marmot and his book. And this is one of the reviews of it. It said, first off, this book is not an easy read. Well, it's not too bad. Being educated in science is not enough to understand the contents. The book will only make sense to people who actively question everything. That's me. If you studied quantum mechanics and found the explanation of Schrodinger's cat acceptable, this book is not for you. If you believe the magical explanation that light is sometimes a particle and sometimes a wave, don't waste your time with this book. If you're willing to believe the clueless parroting of scientific dogma in colleges and magazines and unable to actively question it, then don't bother reading this. This book will actually show how ridiculous some of the currently accepted explanations are and then offer more rational explanations. Dr. Marmot had many of the same questions I have had, questions to which most physicists have responded, your question doesn't make sense. The questions don't make sense because the current explanation of quantum mechanics is partly or completely wrong. Note that the explanation of what and why is wrong unless you believe in magic rather than the mathematics itself. He explains this fairly well in this book, which is not from a mainstream publisher. I especially liked how he shut down all the explanations as light, as waves, particle, or combinations, and then offered a reasonable explanation of what is happening. Anyway, by the way, Dr. Marmot, he died, I think, in 2005, so he's no longer with us, unfortunately. So all that to say that there's a lot out there, and there's a lot of people on the page that I'm on, which is we got to start going back to the. We need someone out there who's going to openly question what we're being told, and this guy and a number of others have had problems with their career, including Eistein, on that basis. This is 3 books that I'll just mention to you. The End of Certainty by Prigioni, he's Italian, is absolutely worth a read. It talks about these subjects from very much a philosophical rather than a scientific point of view, but it's a good blend of the two. Speakable and Unspeakable in Quantum Mechanics is a technical book by Bell himself, who came up with Bell's inequality and explains it, but only recommended if you're really interested in the technicality of that. The Cosmic Code by Pedrels it's probably out of print now, but Quantum Physics as the Language of Nature, very, very readable and very approachable as a way of looking at quantum physics. And he does actually raise some of the questions that I've raised with you this afternoon about, what's real and what are the limits of observability, as I said, in a very very readable way. But the other one I will mention is the Schrodinger's universe by Wolf. This is the guy that came up with the wave theory, whereby he says basically everything in the universe is a wave, even matter. Matter is effectively trapped waves. And he talks about quite well how the Fourier transform, we call it the Heisenberg principle, explains boundaries of matter in space. It's an interesting idea. The book is very, very readable and very approachable, but I will give you a caution that editorially it's got some issues. There are some grammatical and spelling issues, and it doesn't seem to be at all well edited, but the fundamental ideas on it are definitely worth looking at. Okay, I'm just about finished. I could talk for hours, days, months on this subject, so obviously don't want to, but I will say and just share you with this. This sums up where I think we are in quantum physics right now. So on that point, I'll open up for any questions.
Thank you very much, Peter, for this interesting and somewhat provocative presentation.